Hello, everyone. Thanks for joining us. Today, we have Dr. Vighnesh Vatsal. He's a scientist at TCS Research, Tata Consultancy Services, working in areas of, he's in Bangalore, located in Bangalore, and he's working in areas of robotics, AI, and control. He received a PhD from Cornell University in 2020 in mechanical engineering with a focus on human-robot collaboration. He previously received BTech and MTech degrees in mechanical engineering from IIT Bombay with a focus on automation and control. His research interests span the full spectrum of robotics and automation, including mobile manipulation, grasping, reinforcement learning, and applied machine learning, exoskeletons, and space robotics. That's a lot of things that Vignesh has
Yeah.
worked on, and he's a great speaker. I have had him give talk to my students multiple times, and I'm very happy to have him here. Vignesh, you can.
Yeah.
The floor is yours.
Thank you for the kind introduction, Professor Sandeep. So again, really sorry for the delay, everyone, but we can get started now. Hope my screen is visible.
Yeah, screen is visible, and you're
Yeah.
audible. Yeah.
All right. So in this talk, I've titled it "From Theory to Practice: Bringing Robots into the Real World." So this is a compilation of insights that we've obtained, like through research, theoretical research, simulations, as well as some industrial perspectives on robotics. So what does it take to actually execute robots in the real world? So I'll start with a snapshot of robotics today, what a robot is, how it looks like. So in the media and through news articles and research papers, what you think of when you think of a robot is something like this, either a humanoid or a mobile base or a mobile manipulator, a quadruped, even something like a surgical robot or robotic arms that do manufacturing tasks, or even agricultural robots. These are various embodiments. Now, some more exotic embodiments are in deep space, in micro robotics, underwater robotics, as well as wearable robots in the forms of prostheses and exoskeletons. And then you have the whole gamut of household, so to say, robots like the Roomba and social robots. And I guess the most functional form of what can be considered a robot in this sense, where a consumer would directly interact with, is a autonomous taxi like the Waymo, the self-driving cars. So one of the more philosophical questions that this brings up is what counts as a robot? So is your smart fridge a robot? Is your smart espresso machine or a smart home automation system of this kind, where you're able to control everything in your home through a central server? Does that count as some kind of a robot? So for that, you have to go back to the definition of robotics. So if you think of this typical hierarchical iterative paradigm of robotics, which is sense, plan, act, take in information from the environment, figure out what you want to do, and then perform that action. So in that sense, even a smart home can be maybe people might disagree in calling it a robot, but it uses the same principles, at least when it comes to a systems approach. So when it comes to these kinds of approaches, that the sense, plan, act loop is not the only way in which you can do this. So you can so this kind of breaks down the functional modules that are involved in the plan part, at least, so the forward loop. Or you can have a reactive paradigm where there's no time-consuming intermediate planning step, where you just go from sensing to action in rapid succession, kind of like a reflex system of the human body. Or then you have a hybrid paradigm where planning is disjointed temporally from sensing and acting. So now let's look at building a robotic system. So now that we know what the paradigm looks like when you talk about robotics of the system architecture itself, now we look at what the embodiment is, what the components are. So the way for building a robotic system is to obviously first narrow down the problem statement, because unfortunately today we can't build a single robot that's able to do everything, which, I mean, a single human also can't do everything without the use of specialized tools or equipment or infrastructure. So in that sense, we should think of robotics as purpose-driven. So you find the hardware required to solve that particular problem. You model the interactions as closely as possible. So for example, in this peg and hold task that I've shown here, you want to model the interaction between the robot, the workpiece, and the I would say the peg, which is your workpiece, and the target, which is kept on the table. So when you model this in a simulator, you don't care about what the room is in which you've kept it or the building. Your environment, your entire world is just these three items kept on a flat surface. So within that constrained environment, you should design the system architecture to execute that problem and build and integrate each module. So one of the key things that has happened today is you're able to test all of this in simulation before transferring it to the real world. So this is something you can do iteratively, train in simulation, test in simulation, then transfer it to the real world and perform another round of testing and training if necessary to get the best possible outcome. So I'll just touch upon something about simulation in robotics. So this field has expanded tremendously in the past decade or two, where we're able to now create these high fidelity environments of a wide variety of physical systems, like you see here, your classic pick and place with a robotic arm, underwater robots, soft tissue mechanics. So for surgical robots and other such devices, you need to be able to model the interaction with human tissue. So that is now also possible with the current generation of simulators. Then you have simulation for really dexterous tasks like grasping or locomotion for legged robots. So the question for why simulate is that it allows you to look at each of these aspects of your robotic system and try them out before you create a physical embodiment of that system. So just a snapshot of what I would say counts as simulation. So for mechanical design, you have obviously your usual CAD tools, finite element analysis, kind of software that's available. For control systems, you have things like Simulink, where you can model the entire control loop and get your desired performance in the simulation. And Simulink is also able to transfer to hardware quite easily these days. Then you have more sophisticated simulators with wider environments, such as Gazebo and PyBullet and Mujoko and Isaac Sim and other such class of simulators, in which you can perform task and motion planning. So for example, in this task that you see here, the goal would be to pick this yellow object and put it on the table, and pick this red one and put it here to correct this kind of an anomaly detection problem in a retail type of setting. So instead of training your task and motion planner on a physical robot, you can do this in a simulator and achieve better performance by speeding up the iterative design process. Now, field robotics is another key area where simulation plays a big role, because most people don't have ready access to, let's say, rugged terrains or deep sea environments, or even drones to test out their flying algorithms. So for all of these settings, you have now dedicated simulators to help you design your controllers and your planners and all the other algorithms such as vision and like a systems level architecture design can be done in simulation before even starting work on the physical system. So when it comes to robot learning, which is a really popular topic these days, which lets you perform these reinforcement learning or other supervised, unsupervised deep learning type of activities in simulation again before transferring to the real robot. So this is a snapshot of Mujoko from about a decade ago, where one of the early tasks was to train these walker robots in Mujoko using reinforcement learning to walk along this racetrack. And from there, we've come a long way as a community, where using deep reinforcement learning, you can train thousands of robots to learn to walk in parallel, also by randomizing the domain in which they operate, so that the real system, when it encounters a certain scenario, a certain terrain, it's able to perform its job. So this is work from ETH Zurich. Yeah, so this is the key thing, the sim to real transfer. And once it's trained in simulation, then you try it out on the real robot. So as you see here, if you train the policy with enough variations and randomness in the simulator, it can handle things like this, where the boxes move randomly, which is really hard to add into a classical controller in a deterministic way. So when it comes to reinforcement learning, I'll talk about one of the problems that we looked at, which is vision plus RL for soft robotic grasping. So for those who may not be very involved in this field, reinforcement learning is basically a paradigm in which you have your agent, which is the robot, that performs certain actions that influence the environment. So the environment here is your tabletop system. The entire setup that you see here counts as the environment. So your agent performs an action that influences the environment. The states of the environment are then tracked and fed into the agent, as well as a reward function is obtained from the environment. So this reward function regulates the actions that your agent will perform. So in that sense, this loop is executed over and over and over until your agent has a policy that is able to maximize the reward. So it's able to perform the actions that maximize the reward from your environment. So in this case, for soft robotic grasping with reinforcement learning, what a high reward would be if the robot is able to pick this target object and place it in this target area successfully. So this project involved a bunch of components: vision-based grasping, soft robotic grippers, simulation of soft grasping, and RL for grasping. So now vision-based planning is a quite well-studied field, especially for two-fingered parallel jaw grippers like the ones you see here. So DexNet 2.0 was one of the highly cited papers in this domain, where you basically take a depth image of your target object that needs to be grasped, generate these grasp candidates from which the robot can approach the object, and then rank those grasp candidates based on a convolutional neural network architecture to find the most robust grasp and then execute that grasp. So this same paradigm has been refined and applied, extended by lots of research groups over the years, where people have made it real-time or a closed-loop visual surveying method for grasp planning, so that if there's any error in the grasp execution, that can be corrected in a closed-loop manner. So if vision-based grasping is already this well-studied, why are we doing this now? The reason is that soft robotic grippers present unique challenges. So grippers like the ones you see here for handling these fragile or deformable objects, especially in retail kind of scenarios, the physics of these is not easy to simulate or easy to create these kind of deterministic grasps. So for example, in a two-fingered parallel jaw gripper, the only thing you need is a grip width, which is the ones you see here in red. While for a soft gripper, you'll need to model the entire continuum mechanics of this piece of rubber or fabric or silicone, whatever the deformable material that your gripper is made of. So there have been efforts in trying to simulate these soft robots with various degrees of success. So there are a bunch of simulators out there purpose-built for these scenarios. Now, of course, the current iteration of Mujoko and Isaac Sim are also able to simulate soft bodies within the same environment. But the motivation for applying RL in this work is that training in simulation allows for exploration of a large number of grasp strategies. So the two-finger grasp strategies of just grip width alone will not work, because you need to control the whole finger. And the existing RL and vision-based planners have shortcomings, because they're catered for suction-based or parallel jaw grippers. And the planners for soft grippers that were there up until we did this work about 2 or 3 years ago were generally trained on physical systems directly. So you got your feedback signal directly from like physical experiments. So that didn't allow for a lot of exploration in the reinforcement learning training loop. So what we're doing is training a reinforcement learning agent in simulation to perform grasping with these soft robotic fingers that we've also simulated in this spy bullet environment. The task is simple. It's a top-down pick-and-place grasping with a 6 degrees of freedom robotic arm and a 4-fingered soft gripper. So this is the overall architecture. We use one of the CNN-based models for two-fingered grasping as an input to the RL model, as one of the inputs. Then we're tracking the curvature of the fingers and the state of the robot as well while we're performing this activity. And then the action from the RL model is the grasp execution. So I won't go into too many details on GGCNN. You can look it up if you want. So that is basically just a vision model that gives you grasp poses around an object of high quality. Now, while simulating the gripper, the key thing that we're interested in is the curvature of each finger and the torsion of each finger. So both of these quantities change when the gripper interacts with an object. So instead of tracking each of, like, discretizing the continuum mechanics of each finger and then tracking those individual elements like an FEA problem. We instead chose to look at these bulk metrics of curvature and torsion to make the problem a little easier. So in this case, our RL agent is a soft actor critic trained using soft actor critic algorithm. The simulation environment is what you saw earlier. The states are the state of the wrist, the grasp vector from GGCNN, and the curvature and torsion of the fingers. The actions are the movements of the wrist, like the height and angle of the wrist, and the finger vector. So the amount by which each finger is actuated. The reward function prioritizes completing the task. So picking this object and placing it on the target area, lifting the object successfully from the table, as well as a measure of overlap of the fingers with the object in terms of contact dynamics. So the idea was that if all of your fingers are in contact with the object up until, so as much as possible. So if the whole length of the finger is in contact with the object, that's a higher score. So because that would imply a more robust grasp. So we trained this model with a soft actor critic agent for about 20,000 steps. And we were able to obtain a decent improvement upon a baseline, which was just a vision-based grasping with synergy. So all 4 fingers opening and closing by the same amount at the same time. So here you can see a video of it in action. Yeah. So we demonstrated this simulation pipeline for training an RL agent for soft grasping. And further improvements are needed, definitely. So we can now use the latest tools to model the interaction to a closer degree, as well as try out the newer generation of RL algorithms as well. So I'm sure we'll be able to improve upon the performance that we demonstrated earlier. So in this exercise, we also created a prototype of a soft robotic gripper intended for retail use cases. So this gripper has a reconfigurable finger. So you can go from this kind of a triangular configuration to a cylindrical configuration as well. So you'll see that in just a moment. Yeah, so this triangle configuration is good for spherical objects. So one of the fingers can rotate about its hinge. So this was after the previous works where we had a 4-fingered gripper. So this is now a 3-fingered gripper. So here you see the fingers had a different configuration for a cylindrical target object. Right. So all this was in service to a retail automation system, which is a mobile manipulator robot with 2 different kinds of grippers mounted on an omni-wheel platform that was developed by our team at TCS Research. The idea here was to have this full stack of navigation, perception, manipulation within the robot and directed towards this retail problem. So one of the ways we're collecting training data for automation is through teleoperation, joystick-based teleoperation, as well as an anomaly detection module. So here, what you see it in action where the Lay's packet was highlighted in red, saying that it's out of place in this shelf. So that's what the robot should focus on, should pick out of the shelf. So here it's through teleoperation by this person here through the joystick interface. Yeah. So before I move on to the next section of human-centered robotics, I can take any questions quickly for whatever I've spoken about till now.
Vighnesh, I think we can carry on.
Okay, I guess we leave questions till the end.
Unless if someone has a question, they can raise their hand, but I don't know.
Okay, sure. So now we come to human-centered robotics. So robots and humans have been operating around each other in various ways across history, starting from the classical manufacturing robots in the automobile domain. So there are various abstractions of human involvement that you can think of when it comes to human-robot interaction. So in settings like crowd navigation, the human is more of an obstacle for the robot instead of a collaborator. So here the robot has to think of the human as something to be navigated around, as something that is getting in its way. Then you have shared autonomy, in which the robot and human are both performing the same task together. So there is some form of control moving from the human to the robot, and but the robot is still performing the task in its own workspace. Then you come to shared physical workspace, where the human and robot are doing the same task with the same shared workspace. So here, the human and the robot are, for example, doing a kind of construction task, sawing wood together. Then you have wearable robots, which is one level further, where humans and robots essentially share the same bodies. So all of the forces that the robot applies and are transferred to the human body, and the human can change the state of the base of the robot while they're moving. So it's a much more tightly coupled interaction. So in this case, when you look at biomechanics and robotics, so biomechanics is the study of the human system, particularly when it comes to the musculoskeletal system, muscle skeletons in anatomy and the medical domain. But when you tie it with robotics, in this case, it's the robot that becomes the abstraction. So you're more interested in looking at the human body and studying how the robot influences the human body while the tasks are being performed. You, of course, want to control the robot as well if it's a motor-driven robot. But the bigger consideration here is to focus on the human, because your safety becomes a huge factor in these scenarios. So one of the things I'd looked at during my PhD was how a wearable robot can affect the user. So looking at these kind of shared tasks and studying the biomechanics of interaction between the robot and human. So one of the things that I explored was, how do we find motions for the robot? So in this case, it's a wearable robotic arm that's mounted on your forearm. How do we find trajectories that minimize muscle loads? So I won't go into too many details on this, but basically we used a stochastic trajectory optimization approach with this biomechanics simulator. So this was OpenSim running to evaluate the muscle and joint torques in the human body. So with that signal as an input to the stochastic trajectory optimizer, we were able to find motions for the robot that minimize loads on the human. So since then, Mujoko and other simulators have had advances in biomechanics simulation as well. So MyoSuite is one of the more famous libraries based on Mujoko for biomechanics. So we're able to model these really sophisticated human systems in a near real-time fashion in MyoSuite. So once you have that, what you can do is add a robot on top of that system and perform, look at this entire human-robot interaction model in simulation and perform closed-loop control of the robot as well, while performing a motion such as walking or running. So when you look at it all together, you have Mujoko and MyoSuite providing the simulation platform so that you can look at human biomechanics in a more granular fashion. You have redundant manipulators in human wearable devices, so those can also be modeled in these simulators. You can do all of your RL and deep learning approaches for gait and behavior design to help train these robots in the simulation. And what you can also do is use this simulation and biomechanics data to improve the design of, let's say, passive exoskeletons. So simulation as a whole is an integral part of the entire design, control, interaction, evaluation, deployment, all of those pipelines. It really plays a key role. So here I want to talk about one of the things that was published from our lab at ICRA 2025, which is the design optimization problem, as I mentioned. So when you take passive exoskeletons, so these are two exoskeletons that we took from literature. One is a shoulder support device, one is for walking, so hip and knee support. You take these baseline designs and you can use simulation to optimize these designs so that they would be more useful for people when they perform real tasks. So this desired task motion that you see here comes from motion capture data of industrial workers performing their tasks in warehouses or construction facilities or manufacturing facilities. So that task motion is tracked by a pre-trained RL controller on this MyoSuite model. So the human system is also moving using an RL-based controller, as well as the signals from this, the forces and torques from the biomechanics performance evaluation are fed into a design optimization module, which also uses RL to find the best design parameters for these baseline exoskeletons that we looked at. So once this loop runs over and over again, we're able to find a design that is more suited for a particular worker in a specific domain. So what tends to happen in exoskeletons specifically is that they're designed for a single task, or they're designed not keeping all the ergonomics into account. Or sometimes what happens is, if for example an exoskeleton is designed for lifting, the person can end up fighting the device if they bend down to pick up something. So you don't want that to happen. So our idea was to use a design optimizer to find an optimal exoskeleton for users and workers in these domains, so that they end up actually using the device and not feeling like they're fighting against the device. So this was all in simulation, of course, but we're moving to testing these out in real world scenarios as well with passive exoskeletons. Now, as I mentioned, simulation is a powerful tool in across domains. So one of the other problems that we looked at was on-orbit space robots. So this is a debris capture problem where you have a robotic arm mounted on a satellite, and you want to capture this floating piece of space debris. So all of this was again simulated by us in a PyBullet environment, where we were able to train a model predictive controller for whole body control of this satellite manipulator. As well as, so we're also looking at humanoids, where we're applying these same principles of simulation, sim to real, domain randomized reinforcement learning training for the humanoid problem. So this is now currently a really popular topic in robotics, where people are expending a lot of effort, both research and commercial effort, in creating humanoids that are actually useful for certain tasks. So some of the lessons we learned over the years are, you should simulate what you can, because simulation lets you train and test all of your planning and control algorithms before moving on to a physical system. Try often and fail often. So there's really no other way for a robot to be effective in the real world than iterative refinement and narrow down the problem. So what you see here is the video is from the DARPA Robotics Challenge, where these humanoid robots were supposed to do an inspection and safety kind of tasks. So the thing that you see here is the blooper reel, the failures that were encountered during these tasks, because of the last point. So you need to over-design to account for real-world uncertainties. So if your motor fails while performing a task, if a communication gap happens, if one of your CPUs goes offline, the robot can fail catastrophically. So when you design robots in the real world, you need to take all of those uncertainties into account and kind of try and design around them as much as you can. So of course you can't account for everything, and putting in too many checks and balances and redundancies is also expensive. So there comes a point where you need to be okay with certain failures. So in that sense, you need to design your robot chassis in a way which a lot of these humanoid companies do these days, where even if it falls down, there's zero to minimal damage of the physical components of the robot. So that is one of the ways in which you handle real-world uncertainties, just through passive design, because you can create fail-safes for a lot of things, but what you cannot create for is something that you should account for in other ways. But the point I'm trying to make is that robotic systems design is very different in that sense from computer systems design, where things happen in the virtual world largely, so you can adapt on the fly and change things while they're running. That's much harder to do on a robot. And once you do discover a failure mode, if you want to correct for it in a future version, you need to do the second thing, try often, fail often, do the iterative redesign. So that is one of the big lessons that you should take away when designing robotic systems, that things that have interactions with the real world is necessary to design them with greater factors of safety and greater accounting for real world uncertainties than purely computational or virtual systems. So the way forward, as I'm sure a lot of you would be aware, is these general purpose robots via foundation models. Everyone is looking at these technologies these days, where you have multimodal data coming into a foundation model and then being transferred to various embodiments. And one of the main challenges in this is the scarcity of high quality data, which is being tackled by large scale data collection activities by multiple companies right now. The uncertainty and safety is not fully solved. So the foundation models, if they mess up with text, it's one thing. If they mess up in the real world, that is a much more dangerous scenario. So you want checks and balances on the outputs of these foundation models for robotics specifically. So future directions are more embodiments, cross-embodiment transfer, taking in the dynamics of the environment into account in simulation in your foundation model through world dynamics models, grounding it and continuing learning. So grounding is basically making sure that it operates correctly with your physical environment. So now that we're getting towards the end of this talk, I'll just go over how you can get involved as a student, as a researcher. Is that robotics is inherently multidisciplinary, and all of these fields are relevant to robotics. So you can be a mechanical designer, control systems could be your area of interest, electronics, computer vision, machine learning, and AI is right now the big thing that is attracting a lot of funding and research effort. But everything associated, such as computing architecture, energy storage, better batteries, all of those play a role. And when it comes to human robot interaction, specifically biological systems knowledge, psychology, sociology, and looking at how these robots are received by the user, are designed so that they can designed in terms of behavior so that they will be treated as collaborators and not as a risk or a dangerous element in your environment by the typical human user. So all of those are important factors now when robots are going from just segregated into factories to now into our daily lives. All of that will, all of these fields will play a role in creating the next generation of robotics. So essentially, if you are interested in robotics and you come from any of these domains or more, it's a broad tent. You can contribute to this field with any expertise that you possess, essentially. So that's all from me. Thank you, everyone.
Thanks, Vighnesh.
Yeah.
So the floor is open for questions.
Yes.
Hi, Vighnesh, I have a quick question.
Yeah, please.
So you spoke about the foundation models and for foundation models for robotics and all. So one thing you mentioned is the data is the bottleneck.
Yeah.
But what other aspect of robotics do you think would be the bottleneck? Like, is it perception or manipulation, or have you thought on those lines? Yeah.
So when it comes to manipulation specifically, that people are counting data as one of the bottlenecks for manipulation, because you don't have very high quality trajectory data, high quality haptics data, for example, that is needed by these foundation models. So for perception, I mean, that is, I feel, a completely, that is its own domain. That is from the computer vision people. Whatever new technology, whatever improvement they do, that is pretty much directly applied to robotics. So that, I feel, is more of a.
But perception has part of actions included in it, right? Like partly what I'm talking is like the, I would say perception comes with vision and some action included.
Right. So that is what the thing you see on the left here. You have your various modalities coming in. Yeah. Again, this data is also very sparse. We don't have good, COCO data set, ImageNet. We don't have that for robotics.
Are there any ways that we can actually bypass this requirement for data? That was my
Right. So that is what that was one of the criticisms for foundation models, where why are you relying on just data when you have really good theories for system modeling, for from your control systems theories, where if you're able to, for example, build a tactile or proprioception system through classical approaches, then why do you want to feed that information as well into a foundation model? The point is, give the foundation model the data that is available and do everything else with existing methods. I mean, that is one paradigm that I've seen, so that everything is not end to end.
Okay. So, Vighnesh, I have one question. So in image or a sound or whatever in other domains, so foundation models plays a role. So for robotics, do we really need it?
That is a good question. No one, I don't think people have answered it convincingly one way or the other. I think what excited people was about foundation models was that once you have a single kind of generalist model, it is able to perform multiple tasks across multiple robot morphologies and embodiments. So that is the holy grail that people are chasing when it comes to foundation models. Now, whether or not that will be successful, to what extent it will be successful, is pretty much an open problem right now. Like, I can't comment either way. But what we have already solved successfully, for example, you shouldn't apply a foundation model to basic locomotion or to flying a drone, because A, it will be more computationally expensive, and B, it might not give improve performance more than your typical MPC loop. So there is also this question of trying to find a problem for a solution that is happening in robotics when it comes to foundation models, where you're applying this to things that are already pretty much solved.
Yeah.
Yeah.
So
That is something
Vignesh,
that,
just a question to add on to that.
yeah.
So how do you like? We have been working. We all have been working on generalizable solutions, right? Like models, we want RL models to be generalizable for either like the domain changes or your vehicle itself changes or maybe fault recovery or something like that, right?
Right.
So these are mostly generalizable models we have talked about. Like how do you compare that with foundation models? So, like why are we just calling it a new name, or is it just that, or
So
what is the difference?
I think the nomenclature obviously comes from the AI community with ChatGPT.
Yeah,
And
I know, and it's also attractive because
yeah,
everyone is
yeah.
excited
So
about it.
that's what gets you your funding when you use these buzzwords. But uh, conceptually, I would say there's no difference in that sense between a foundation model and a general purpose model. So, like the way we looked at RL until now was in a single task, a single domain, single embodiment largely. Uh, I would say foundation models is just a scaling up of the generalization of RL.
Okay. But people have looked at like more generalizable RL models also, right? Like, yeah.
Correct, correct.
Anyway, yeah,
Yeah.
I agree.
I'm saying foundation models, the thought process, from what I can tell, was to bring it one level higher, like one more order of magnitude of generalization.
Make it more abstract. Yeah.
Yeah.
Any other questions? Okay. So Vighnesh, just one last question, since you worked a lot on manipulators and hands.
Sure.
So, but is the way the manipulator is designed for it's trying to primarily mimic the way the human arm does, right? So, is that the optimal way for a robotic to do?
Depends on the use case. So people build these degrees of freedom robotic arms because they have a certain dexterity, and they were able to perform essentially certain kinds of industrial tasks very well. And because in the real world you want 6 degrees of freedom of your end effector, so thought process is you want to have 6 or 7 degrees of freedom, or for redundant manipulation. Definitely this is not the only embodiment that is possible. You have parallel manipulators, you have SCARA type of manipulators that are purpose built for specific applications. So for example, the Delta robot, which is a parallel manipulator, looks nothing like any human or animal, but it's able to perform pick and place tasks at a speed, like milliseconds per task in some cases. Not milliseconds, I would say like tens of milliseconds.
Okay.
So yeah, you can, I mean, any embodiment I think is created backwards from the use case and the applicability in the real world.
Okay.
Yeah.
Okay. Thanks. Okay. Looks like that's no further questions. Thanks, Vighnesh.
Yeah,
for the wonderful...
actually, I would like to ask one question because
Okay.
Yeah,
Please
so
go ahead.
yeah, so you shared one slide regarding you published in ICRA 2025 that passive
Right.
skeleton and that RL.
Yeah, let me just pull it up.
Yeah. So like in this, have you done like, I mean, this study was entirely based on simulation, or it was really performed in lab? Because I can see it was, I think, done in OpenSim or Mujoko.
This is Mujoko, MyoSuite.
Yeah. So I mean, I just wanted to know more about this. I mean, can you please explain it more, like how you have done this, and is it possible to publish this kind of thing by doing just simulation in research papers?
So when we did this exercise, there weren't too many similar works out there that had looked at this specific problem setting. So I guess that is why it was accepted even as just a simulation result.
Yeah.
Today it would be much harder to even get this published because there is a lot of simulation work also out there.
Okay. Yeah. So that is what I thought.
Yeah. So today you'll have to do this plus validate it on a physical system to make a convincing paper.
Correct, sir.
Yeah.
Okay. So thank you.
Okay.
All right.
Thanks, Vighnesh. Thank you very much for your wonderful talk.
Right.
Thanks, Vignesh.
Yeah.
Thanks
Thank you
all for
joining.
coming for the talk, joining for the talk.